So yeah, hi everyone. Thanks for joining us today. So it is my great pleasure to introduce you to our speaker today, Dr. Fei Gao. So Fei is an assistant professor at the Fred Hutch and former postdoc in our department. And before that, she got her PhD in biostatistics at UNC Chapel Hill. So her research interests include survival analysis and semi-parametric inference, but she's also interested in causal inference and the design and analysis of clinical trials. And I guess from the title, that's what we'll hear about today. So yeah, Fei, thanks for being with us today, and we look forward to your talk.
Great, thank you. Thank you for the introduction, and thank you for inviting me to speaking here. And it's really my great pleasure to be able to talk as you last again after spending some time here. So today I'm going to talk about this project design for HIV prevention trial with counterfactual placebo instance based on recency test. So here is an outline of my talk today. So I will first introduce this background HIV prevention trial and also instance estimation with recency test and our whole proposal of using recency test as one factor of counterfactual placebo. We'll then introduce how to apply this and some sample size calculation perspective for applying this in active arm trial first, and then we'll discuss how to extend this approach to a more realistic active control trial in HIV prevention. And I will conclude with some final remarks. All right, so for HIV prevention, the past decades have seen tremendous progress in the development of biomedical agents that are effective as the so-called pre-exposure prophylaxis for HIV prevention. So specifically, in the past development, Truvada and Descovy, there's two pill. So you can intake it as pills. So this type of drug has been authorized for use as PrEP for HIV prevention for years. And based on their clinical trial development and also evaluating of their efficacy in various populations, they have been shown high efficacy in different populations. However, their efficacy may depend on whether subjects would intake them with higher adherence, say, for example, if you can take them daily or as prescribed. So recently from recent HIV prevention trials, for example, HPT and OA3 and OA4, so cabotegravir or so-called CAB-LA has been shown highly efficacious compared to Truvada. So we already have a lot of progress in development of all those agents that are effective to prevent HIV. However, there's still need for new PrEP agents in that, for example, we may want this drug to be long-acting so that subjects do not need to really take into pills every day. Or for some other reasons, for example, some subjects may prefer one type of prevention methods than the other, or we may want to avoid some certain sort of side effect. Therefore, we may need to evaluate those new PrEP agents. And also, we may consider a new regulatory framework to try to evaluate them. However, designing trials to evaluate those new agents may be challenging. One thing is that given current setting for HIV prevention, original placebo-controlled trials are no longer ethical, since we cannot really randomize participants to receive placebo, given that we know there are already lots of products that may be beneficial for this patient. Therefore, the traditional design will be try to demonstrate superiority or non-inferiority versus an active control, for example, existing drug, Truvada, or even existing injection methods, CAB-LA. However, this kind of trial of superiority or non-inferiority, they're likely to be very large because current methods are likely to prevent really a lot of HIV infections. Therefore, in order to compare these two products, the power will rely on how many cases we observe in each arm, and the number of cases seems to be small. So we need to, given that current methods are highly effective, therefore we may need a large sample size or large number of years of follow-up trying to collect the signal we need. This motivates another approach, that is, what if we can have another measure of efficacy that compares how much HIV instances we can we can prevent comparing to placebo groups. Specifically, we call it counterfactual placebo because we cannot have a placebo group in the trial, but rather we want to use other type of information to construct a counterfactual placebo, one that approximates incidence for randomized concurrent control trial group receiving no PrEP. So to construct this type of counterfactual placebo, there are some existing type of ideas. The first idea is based on external placebo. So basically, since we cannot have a placebo group in this ongoing trial, maybe we can use HIV incidence data from recently completed trial with the same size or comparable size. And there are already some practice on using this type of approach. However, one shortcoming of this approach obviously will be like in the long run, in the future trials, there will not be as many recently completed trials without PrEP use compared to what we have for now. Another type of approach is to use the so-called sexually transmitted infection correlates. And this idea has been proposed by Malik and Mori in 2020. So basically the idea is simple. If we have some STIs that's associated with HIV, but they are not affected by PrEP use, then we can use that to be used as exposure marker of exposure. Therefore, if for those subjects in the trial, we observe their HIV instances receiving the new PrEP agent, and we can infer their placebo instance based on their STI instance, then we can use that to come up with an efficacy measure for HIV for this PrEP agent. And here is the final idea we're going to explore more in this talk, that is to use recency test. So by the title recency test, it is a recency assay or is a collection of recency assay trying to detect recent infections in samples. Suppose that in the screening population, we're able to apply this recency test so that we can make use of the so-called cross-sectional instance estimator to determine the instance in the screening population. So I will introduce this idea more clearly later. But suppose that we are, based on this recency test, we are able to collect an instance in the screening population. And by default, the screening population have not already received this PrEP agent we're going to apply it in the future. And also for this population, maybe it'll be free of PrEP, or it will be like only using the standard of care PrEP. This estimate will serve as a counterfactual placebo HIV instance for this trial population. Okay. So then I'll spend some time trying to give more idea of how we can use this recency test results trying to infer instance. And also I'll try to introduce more about what type of assumption we need so that this instance estimation based on recency test from the screening population can serve as a counterfactual placebo instance for the trial population. So here is the question. We suppose that we have a cross-sectional sample of subjects, and in our setting, it will be the subjects who come to screening. And then we may have some information from these subjects, and based on those information, we would like to determine the instance for this population. Suppose that for this collection of subjects, the HIV infection status can be accurately determined. And then we may further apply a biomarker-based algorithm, so-called this recency test, to determine whether the infection were required recently. So this idea have a long history in HIV, and they were first proposed using diagnostic tests for HIV-1 P24A antigen, such that those who are antigen positive are classified as recently infected. Therefore, by counting how many subjects are indeed recently infected, then we may try to give a rough estimate of this new infection in this short period of time. So however, for P24 antigen, this period is relatively small, so that we really need to look at a lot of HIV infected subjects to determine the agent, the instance. So later on, other testing algorithms were proposed based on different property of different biomarker after HIV infection. For example, HIV enzyme immunoassay, antibody availability index, or genetic diversity. So in our development, and also in HIV, right now, the currently most popular recency assay is based on this antibody ability index, and maybe it can be combined with other markers such as viral load to have a better property. So for a sample of big N subjects, suppose that N pos and N neg, they are a number of HIV positive and HIV negative subjects. And suppose that among these N pos HIV positive subjects, N reg of them are identified as recently infected by the recency test. Then we make use this information to estimate the incidence in this cross-sectional sample given as here. So basically, we have several parameters that come into play in this formula. Specifically, T star, here is a cutoff time to determine whether this recent infection occurred in between T star, occurred up to T star from now. Usually this T star is set to be 2 years. And then in that case, this incidence estimator will relate well to the average incidence from year 2 prior to this current time. So our other relevant estimate parameters are omega T star, which is the mean duration of recent infection, which is MDRI. So it is defined as the mean duration of recent test positive for HIV positive subjects infected less than T star years ago. So another way to think about this is like a summary measure of sensitivity, and this summary measure is related to time, because here we try to consider a period of time. So for subjects infected less than T star years ago, so these are subjects who are truly recent, and this omega T star is the average measure of sensitivity among all those subjects. Another parameter is beta T star, also called the false recency rate. It is the probability of recency test positive for randomly chosen long-infected subjects, and it is relates well with the test specificity of this test. So based on all those parameters, we are then able to come up with this cross-sectional incidence estimator that help us to estimate the incidence. Specifically, in the numerator, we have the number of recently infected number of identified recent subjects minus the subjects that may be falsely identified as recent, determines as beta T star times N pos. While in the numerator is something related to basically like the total person year HIV negative subjects will spend in this recency period. It also relates well to the maximum likelihood estimator of a cross-sectional samples if under certain assumption. But if I will have a slide on more technical details on that if you're interested. So note that this limiting value of lambda hat is a weighted average of recent infection in between negative T star to this current time under the assumption of constant prevalence. Therefore, when this incidence in the period of T star prior to screening can be viewed as constant, this cross-sectional incidence estimator will be unbiased for estimating incidence in the screening population. Therefore, this assumption we need will be like a constant incidence and constant prevalence over this period of T star equals 2 years. And it will give an unbiased estimation for the incidence in the screening population. So this helps us solve the problem of what this estimator is estimating, but we still have this final linkage to the counterfactual placebo, in that we want to link this incidence in the screening population to the incidence that we may observe in the trial if the subjects will be given PrEP, will not be given PrEP. To serve as a counterfactual placebo HIV incidence for the trial population, we would then require certain similarity between the screening population and the trial population if the subjects in the trial population will not take PrEP. In that case, first of all, we want to have this willingness to HIV screening is independent of HIV status. So this first assumption basically saying that the screening population is a representative sample of the whole population we are interested in. So for example, if we have subjects who are known to be HIV positive, who will not come to screening, in that case, this incidence is estimated from this screening population would be an underestimation of what's going on in the whole population. In order to fulfill this first requirement, we would definitely need to have some sort of adjustment of current study screening procedure, in that we want to have this co-screen population to be as close as the whole population as possible. The second set of assumption is in terms of HIV risk, especially comparing those in the screening versus those who will be eligible in the trial. Specifically, we want to assume that no symptomatic difference between HIV risk of those in the screening population and those eligible for the trial. Specifically, for example, if there's an additional eligibility criteria for being included in the trial, for example, if you are free some chronic disease, we would like this eligibility condition to be applied prior to the screening. So basically, again, it will require a certain change of current screening procedure as well in order for this to be accomplished. Or otherwise, we may want to apply some further adjustment to make sure that the systematic difference between HIV risk of those in the screening and those in the trial population can be adjusted using some collected covariates. Finally, we need to require that incidence is constant or can be approximately seen as constant over negative T star to tau, where tau is the follow-up time in those not taking PrEP. So this will be like easier to understand in that here for the counterfactual placebo, we're estimating what's going on in between negative T star to current time, but the trial actually starts from current time to tau. So we would like to have a constant instance over time for those not taking PrEP, so that what's going on prior to the trial start can be applied to the later on trial. Okay, so now we will come up, I have introduced this estimator we're going to use, and later on I will move towards this trial design components, making use of these estimators. But before now, I would like to pause a little bit and see if you have any questions.
I have a quick question.
Sure.
When you say placebo arm, do you actually mean like a counterfactual world in which they like, I guess, like, what does that mean? Does that just mean like because it seems like it's more similar to the actual population that does have access to some sorts of prevention, right?
Right, so here we would like to, I call it counterfactual placebo because, and also it's a counterfactual placebo for the trial population, because for the trial population, usually we cannot provide placebo, but rather they are going to take some active treatment. For example, some new product we have of interest, or later I'll introduce, it will be given some other active control drug. So in that case, it is counterfactual because we cannot, they are not taking placebo. But actually, it is the placebo incidence we are interested in, because it will give us an estimate of truly preparing this new agent comparing to a hypothetical placebo arm. So I wonder if that answers your question.
So I guess the thing is you're measuring the incidence among a population, some of which do have access to prevention. Mm-hmm. And so in that sense, it doesn't seem like you're measuring the incidence amongst a placebo group. It seems like you're measuring the incidence among a group that like doesn't have access to the treatment that you're providing for the trial. Yes.
Yeah, I think that's one of the key points of what should be the definition of placebo, right? Because in the trial setting, usually we have the placebo to be defined as we have randomized trial, and we randomize subjects to receive either treatment or placebo. But for here, if we're looking at the screening population, it is indeed a population that subjects. So first of all, comparing to subjects who's enrolled in the trial but maybe receiving placebo, at least they know of like there's a intervention drug that's going on, and also they may have been enrolled in drugs, so enrolled in the trial, so they have some other information related to this additional information collected from the trial. But here we are trying to, indeed, it should not be called a placebo, but rather it's like no PrEP type of instance. And this no PrEP instance will be similar to the placebo instance we'll observe in the trial if other type of factors can be excluded or can be approximated here.
Yeah, I agree that it's like a very good baseline measure. And yeah, I think it's maybe just like tricky to give it a name that makes sense.
Yes.
Concise. Okay.
Yeah, we
Thank
have
you.
done some debate on whether to use placebo, but counterfactual placebo may be like something that have already been used and like people kind of like that. Thank you.
That makes sense. Thanks.
I have a question too, Faye. So actually just on the slide here, so I'm just trying to understand this this estimator. So is this coming from incidence equals prevalence over duration, mean duration? I mean, this is essentially what this formula is trying to do.
Yes, you're right. So it's closely related to that, but actually, yeah, actually at first sight, I found this to be very hard to understand. And since it's not like entirely the focus of the talk, so I didn't really give much detail on this, but maybe I can go to the technical details so like it can be easier to be understood. Okay. So basically here is, I think, one thing that's easier for statistician to understand. That is, we may want to see what's this estimator is about. So basically, one short question is closely related to the maximum likelihood estimator based on this collective sample of collective cross-sectional samples. So for example, if we have P to be the prevalence, and we have, in that case, at the cross-sectional sample for those HIV positive and HIV negative will have approximate probability to be P versus 5 minus P. But for those who are recently, or not, so for those who are test recent, so in that case, it will include those subjects who are truly recent with some probability related to this omega T star, and also those who are indeed long infected, but they have misclassified as recent. So basically, we can write out this probability as this too, where we can approximate those. So suppose that instance is constant and occurrence is rare. In that case, the rate of new infection from negative T star to 0 can be approximated by lambda T star. So in that case, those are subjects who are indeed long infected over time, and we have it to be times this false recency rate. And for those who are indeed infected over this T star period, their probability of being identified as recent can be seen as like omega T star over T star. Therefore, we have this approximate probability. And if you have like all this, you can write out this likelihood corresponds to this different piece of data. And in that case, the maximum likelihood estimator is lambda hat. So it is closely related to this type of test with certain sensitivity and specificity. And also, as you're right, so it's closely related to like having divided by all the cases by the other person year spent in this recency period.
And thank you for that. And when you're talking about incidence here, I've always found the literature a bit confusing because people mean different things by incidence. So sometimes it's at the person level, sort of a hazard, and other times it's at the population level. And when it's at the population level, is it normalized by person time or just by time? And so in this case, is it just by time, so number of cases per unit time?
I think it should be person time, right?
So this is person time?
So sorry, I may not get it. So what do you mean by like number of cases per time versus number of cases per person time? So if we're looking at a certain population and we are looking at a number of cases, that's new cases during a period of time in that population, then the incidence should be like dividing the total number of cases divided by total of person time for this whole population, right?
So I guess, if you talk about the entire country, you can say there are 1,000 new cases per day, right? So it's sort of an absolute for the entire country. Or you can say the rate at which, maybe it's, I don't know, one case per person day, or, so one is really under constant population size assumption, then it's just a multiple of the other. It's one is normalized, the other one is not normalized by the size of the population. That's all.
Right. Yes. So
But
here we're looking at the. Yeah,
Go ahead,
here we're
sorry.
looking at the person time as denominator.
Person time. So when
Yeah,
you,
so
when you,
yeah, go ahead, sorry.
no, I'm just trying to understand this lambda t star. So t star is time, and
Mm-hmm.
so lambda then is going to be number of cases per person time.
Mm-hmm.
And so this is unitless. Okay, yeah, that's right. So which is a probability. You're saying this is
Mm-hmm.
this is an
Yes.
approximating.
Yes. Yeah, here we're approximating this probability.
Okay. Okay. Thank you.
All right, thanks. Okay. So, sorry, I was a bit nervous in the beginning. So hopefully you have understand this whole is estimator of estimating incident and the underlying assumption we're making. So now we're going into the details of how to actually apply this incidence estimator in the active in this HIV prevention trial setting, where we use this Recency test applied to the screen population as counterfactual placebo. So first, we'll start with a slightly simple setting where suppose that in the trial, we only have one arm, that is this active treatment we're looking at. So here is a graph showing this whole procedure of this trial with counterfactual placebo based on this test. Specifically, suppose that at screening, we screen a total of big N subjects, and based on the prevalence of this population, then we have observed N-pos of HIV positive subjects and N-neg of HIV negative subjects. Suppose that we recruit, we can take a Q proportion of HIV positive subjects and give them recency test, and we denote those subjects who receive test to be N+ test. And suppose that we observe a total of N reg of HIV of subjects who test results based on the test. So note that this N reg will depends on a number of parameters. For example, omega T star and beta T star that corresponds to the property of the test. And also we are related, here I call it lambda P, which is the incidence in the counterfactual placebo arm. So for those HIV negative subjects, suppose that for our proportion of them, they will be enrolled in the trial, and we follow them for 12 years of time, such that we observe a total of an event of cases. And here, again, this event will be related to this lambda E, which is the instance of the experimental arm. So based on this collected observed data, we are then able to estimate lambda P and lambda E. Specifically, lambda P can be estimated by this lambda P hat, which is a slight variation of the estimator I've shown before to adjust for this sampling like proportion for those who take recency test. Well, for this trial arm, then we can just estimate it by the simple estimator we always use, that is to divide the total number of cases we observe in the trial divided by this total person year we observe in the trial. Then our goal will be try to compare this lambda P hat with lambda E hat to infer whether this new treatment would have a certain reduction of HIV incidence comparing to this this placebo arm. So here again, I forgot to mention, here we have omega T star and beta T star hat. So they are, so we cannot really know the true value of the test, but rather we can estimate those parameters from some external study, and here you notice that's the hat version. So if we have lambda E hat and lambda P hat, the efficacy of the new PrEP agent can then be estimated by this rho hat equals to 1 minus lambda E hat over lambda P hat. So our precision of this prevention efficacy will depends on the precision of lambda P hat, lambda E hat, depends on the total screening sample size. And this is the whole rationale why we want to, we can, of trial design of trying to find out the total screening sample size n such that to give us certain power to determine the efficacy. Specifically, for this cross-sectional instance estimator, we can write out this asymptotic distribution of lambda P hat, which follows a normal distribution. And again, like for those, for the instance we observed in the trial, we also follow a different normal distribution with certain parameters. But one thing here I want to emphasize that is here for lambda p hat is the variance is not only depending on something that's going to shrink with increased n, but also it have one residual term that is not does not shrink with respect to n. The reason we have this is because we have those two terms that can only be identified with error, but this error of this estimators does not shrink with increased sample size of this trials because those estimates are from some external study. Therefore, we always have this residual term, and in some extreme case, since this cannot decrease with the increasing of sample size n, for some really extreme case, this variance of this lambda p will be dominated by this term. In that case, we cannot really do trial based on this estimator of per-session incidence estimate in some really extreme case because this is very large and we cannot achieve the desired precision however we increase n. So then we may consider the following hypothesis testing for this trial. Specifically, we are interested in the ratio of these two instances, and we test whether lambda e over lambda p equals to m versus the alternative hypothesis will be smaller than m. So here for m, usually for this type of hypothesis testing, we just set m equals to 1, indicating testing whether there is any ever reduction of instance in here. But for HIV prevention, since we usually will have highly efficacious PrEP agent, therefore here the hypothesis testing m is usually set to be way smaller than 1. For example, in our later calculation, we set m to be 0.5, indicating that for designing a trial, we will expect this new PrEP agent to be highly efficacious. And based on this trial design, we would like to exclude this setting of even this new PrEP agent is 50% efficacious. So we would like to have a confidence interval that exclude this 50%. So for this hypothesis testing, we can then able to come up with a test statistic based on the observed data given as here. So we will have in the denominator to be the effect size, and in the numerator is the effect size, and in the denominator will be square root of variance terms. So based on our here the calculation is based on this asymptotic distribution of log lambda e hat and log lambda p hat. Specifically to test H0 with significant level alpha and power beta against specific H alpha. This total screening sample size can be given as here. Again, this is slightly different from the usual sample size calculation we saw in literature, in that we have a residual term, a term that will not shrink with n. So we will always have this term in here to calculate the total screening sample size n. So to show some result here, we list some of the realistic setting we will consider for future HIV prevention trial. Specifically here, we consider 4 different populations, so which are of high risk of HIV, and we may need to evaluate new PrEP agent in these different populations. So we will have South Africa, adolescent girl, young woman from age 14 to 17, from age 18 plus, and South African men have sex with men, and USA men have sex with men. So those different populations will be associated with different combinations of incidence and prevalence. As we can see, for some population, for example, South Africa, MSM, even though prevalence is not that high, but the incidence is quite high. But for some other population, we have really a lot of prevalence of HIV, but the increasing is not that fast. So here for this recency test, we consider to use this so-called lag ability, which is trying to measure the ability index of HIV. And from literature, we make use of this recency test to have lag ability ODN smaller than 1.5 and barrel greater than 1,000 copies per ml. So this recency test will react slightly different for different subtypes. Specifically for subtype C that is dominating in South Africa, this recency test will have an MBRI of 118 days and an FRR to be 1.5%. And for subtype B is 142 days with FRR 1.0%. So here for the trial design, we're considering incidence ratio of 0.2 versus the incidence ratio of 0.5 versus 0.2. indicating that we are, so hypothetically, if under the alternative hypothesis, we expect this new PrEP agent to be 80% effective. And based on this trial design, we'd like to rule out this scenario that is even 50% efficacious. We can consider 0.0251 setting alpha and beta equals to 0.8. And for this setting, we consider like 90% of subjects, so Q equals to R equals 0.9, indicating 90% of HIV positive subjects will take tests, and 90% of HIV negative subjects will be enrolled to trial, and the trial will last for 2 years. So in the bottom of this panel, we see some numbers we calculated. Specifically, this highlighted in blue indicate this calculated total screening sample size for the trial. And another thing we want to look at is this second to last row. It is the number of subjects who will enroll to the trials. As you can see, across different population, this total screening sample size seems to be acceptable. It's about the same, about the range that we can actually do clinical trials. And also for those enrolled seems to be reasonable. And under the alternative hypothesis, we expect to see around like more than 20 events in this in the trial arm, and also like we expect to see like more than 20 events or more than 20 test reason subjects in the screening population. So that's great. Then we will then move on to the more realistic setting where instead of having only one arm in the trial, we'll have 2 arms. So this is a setting that is more practical because we will, so for example, in current setting of non-inferiority or superiority trial, usually we would like to randomize subjects to receive either this new PrEP agent or an active control drug. For example, for NPT and OA3, OA4, we want to evaluate CAP-LA, but also for some of subjects, they were randomized to receive Truvada, like to compare these 2 products. But here in this counterfactual placebo setting, even though we have this, we may come up with counterfactual placebo instance based on recency test, there still added value to have this active controlled arm. So for one thing, we want to have this randomization components in the trial, and also it could give us some safety data based on the trial. And finally, we may also make use of what we observe in active control, trying to come up with a more composite hypothesis or more composite endpoint we can look at. So specifically, this is like the upgraded trial design, where instead of enrolling all the subjects to receive this new PrEP agent, we will randomize them to receive either this new agent or active control. And here we let lambda E again to denote this experimental drug, and we like lambda A to denote this incidence for this active control PrEP agent. And again, we observe an event E and an event A, and we can estimate the instance lambda E and lambda A based on the observed data in the trial. Then a natural question is that here we have 3 different estimators for 3 incidences for different groups, for the counterfactual placebo, for the experimental drug, and for the active control. Then what can we define a win, or what kind of hypothesis will test based on the data? So one option is that maybe we can test E is superior to P. So this new agent is better than the placebo. And also E has prevention efficacy comparable to A. So basically here, A will serve as kind of, and when we have only active arm, this is the hypothesis we're looking at. But here we have this added component of hypothesis, so that we have some protection over like how E is comparable to A. Also, there are other types of definition of what is a win. So for example, here are two other candidates. So the second one is E is superior to P, or E has prevention efficacy comparable to A. So basically the main difference is that here instead of and, here we have an or option. So it will be compared to the first hypothesis. This one will have a kind of having a better chance because it can it would hold if either one would hold. And finally, we may have some other type of hypothesis. For example, E is superior to P and A is superior to P. However, here we would like to evaluate basically the first one because we see there are some potential problems with the rest of the other definitions. So for example, if we look at the second criteria, so it may falsely accept the less efficacious PrEP agent if the efficacy of the active control arm is low due to low adherence. So specifically, in the active control arm, when people were taking our PrEP, they were not adhered to the procedure correctly, so that the incidence is quite high. So in that case, even though A is not superior to P, but E, since it is similar to A, we still accept this hypothesis. Therefore, we're having a falsely acceptance of this less efficacious PrEP agent. For a different story, for the last one, since here we have N A is superior to P, we may falsely reject an efficacious PrEP agent if we find A is not superior to P. So basically, the efficacy of the active control arm is low due to low adherence. Therefore, we may falsely reject efficacious PrEP agents because this active control arm is not doing well. So we would like to avoid all this type of maybe false acceptance or false rejection. Therefore, in this presentation, we're going to evaluate this type of hypothesis, such that we are going to evaluate, define a win if E is superior to P and E has prevention efficacy compared to A. So to formulate that into formula, A is superior to P, we call it H1, means that lambda E over lambda P equals to M. We would like to define the hypothesis as null hypothesis is lambda E over lambda P equals to M1, and alternative hypothesis will be smaller than M1. So again, as we had before, M1 should be smaller than 1, indicating that we are looking at a really efficacious, or expected to be a really efficacious PrEP agent. For the second hypothesis, E had prevention efficacy compared to A, which means that lambda E and lambda A equals to M2 versus smaller than M2. For here, we since usually we know that this active control arm can be highly efficacious. So usually the M2 is set something not so low. So for example, in our later application, we set it to be 1.25, indicating our margin that corresponds to regular use non-inferiority trial. So to test this H1 and H2 type of hypothesis, we may consider a joint test based on this statistic. T1 equals to log lambda E hat over lambda P hat, and T2 equals log lambda E hat over lambda A hat. And this asymptotic distribution can be determined based on the asymptotic joint distributions of all those three estimators. So to further consider the test, we may define the rejection region of the test. Specifically, if we like Z1, Z2 to be the marginally standardized version of T1, T2 under the null hypothesis, then we consider the rejection region to be something like this. So we will reject the null hypothesis if Z1 is smaller or equal to Q1 and Z2 is smaller or equal to Q2. And to have alpha level test and beta level beta power under a specific alternative, we will require this two equation. And for some sort of calculation, we would like to solve these two equations since this C1 and Z2 will depend on the 7SM. So one observation of here is that multiple combination of Q1, Q2, they will lead to the same total type 1 error. And Q1, Q2 is actually chosen to allocate type 1 error between the two hypotheses. So in this later application, we first consider Q1 equals to Q2, which corresponds to allocate the same marginal type 1 error between the two hypotheses, which seems to be like we are giving similar weight to making the mistake between these two hypotheses. But later on, we may have some surprising finding. And here is the subset calculation for the same settings. So in addition to the original hypothesis that's corresponding to comparison of counterfactual placebo and experimental arm, we have this additional hypothesis that corresponds to the comparison of these two arms in the trial. And here I highlighted in blue the total sample size that's come from this one arm versus the total sample size comes from the two arm. And one surprising finding is that, so for the total screening sample size, that's including all the subjects with screen, including those who are enrolled in the trial, will be smaller for some setting compared to those who will consider only one arm. But for some other setting, maybe it's larger. So this is like intuitive, but the other number seems to be counterintuitive because we see smaller number of subjects if we are evaluating more hypotheses and if we are doing a trial with more arms. So we have some answers for that. So first of all, here we're looking at overall alpha to be 0.025, where when we have one arm, it's basically saying that marginally for testing based on T1, we have an alpha level to be 0.025. Since here we identify rejection of the null hypothesis if both hypotheses are rejected. Therefore, these two marginal alpha from this two-arm trial, they're actually greater than 0.025, which seems to be larger than this original marginal alpha from this from the hypothesis in one arm. And also, depending on the setting and hypothesis, we find that one hypothesis may be more highly powered than the others. The specific here is one table when we are looking deeper into the South Africa adolescent girl and young woman with age 18 plus setting. Specifically for the first row correspond to design 1. So it is the setting we have that leads to the sample size calculation in the previous table. The total alpha is 0.025, and we would like to equally distribute this alpha level to the two hypotheses. And in the end, we have this 0.087 alpha level, the same marginal alpha across these two hypotheses. So we would like this total power to be 0.8, but we found that this beta 1, beta 2, which are the marginal power of the two hypotheses, seem to be quite unbalanced. Specifically, this power for the second hypothesis that compare these two compare the experimental arm and the counterfactual placebo experimental arm and active control arm is quite close to 1. Where for the beta 1, that is the one that compares the counterfactual placebo, seems to be quite close to 0.8. So in that case, if we're look at only the marginal test of test 1, so it is basically a test we're doing when we are using only one arm data. So it is having a similar power, but we allow the type 1 error to be so much larger than the 0.025 level we'd like to use for this one arm trial, such that we may it leads to this quite shrinks the total sample size because we really gain a lot of power in the testing of second hypothesis. So this scenario may or may not be something we want to see, right? Because for so by looking at these two hypotheses, we may want to weigh one hypothesis over the other. So we may care more about this comparison of experimental arm versus counterfactual placebo, or otherwise we may consider more from the information of comparing these two arms in the trial. So one thing we'd like to comment here, so we don't have a definite solution here, but one thing we want to comment in here is that instead of specifying overall alpha and equally distributing them, we may want to intentionally allocate marginal type 1 error rates and balance power between the two hypotheses, and possibly reflecting which one hypothesis is considered primary or if both hypotheses considered co-primary. So specifically, we can look at this design 2 and 3 in this table. So for design 2, we have this alpha 1 to be set to be 0.025, and for alpha 2, we set it to be 0.05. So basically, we try to individually specify the level alpha for these two hypotheses, but still we want to have a total power beta to specify this whole hypothesis. So in that case, we have a really shrinked total type 1 error. So we are allowing ourselves to make less mistake. So in that case, based on this study design, and we try to individually specify this marginal alpha, we come up with a sample size that's strictly larger than the sample size we'll see from the one arm. And similarly here, we may consider different sample size, different allocation of type 1 error, and we may calculate different sample size for that. And how to choose whether we can allocate overall alpha will depends on our belief of what hypothesis we're mainly interested in, and which, so it's like whether one hypothesis is primary or they are co-primary. So then I will conclude with some final remarks, and probably I know maybe many of you will have some questions, comments on this, and we may discuss more on that. So in this talk, we consider a novel trial design for evaluating new PrEP agents in future HIV prevention trial, making use of counterfactual placebo incidence rate estimated based on recency test results in the screening population. So our results suggest that, so for the future active arm trials with counterfactual placebo incidence based on recency test, they can be conducted with reasonable total screening sample size and aggregate power to determine treatment efficacy. So it is something that's doable, and we can avoid this problem of really large sample size if we only consider non-inferiority or superiority trials. So we try to extend this trial design to active controlled trial, where we argue that to be deemed acceptable, this new PrEP agent must be superior to placebo and has prevention efficacy comparable to the active control. And finally, this is final remark that even though we propose this for this counterfactual placebo based on estimated from the recency test, it is indeed applicable to other counterfactual placebo estimates. So for example, we have introduced before that we may construct counterfactual placebo from, for example, external placebo and maybe from sexually transmitted diseases. So estimate from those can also be, so we can also apply our approach to to other types of placebo constructed. And the only thing we need to is to construct, adjust the variance estimator or how the estimators would come up with the counterfactual placebo and try to adjust this approach slightly. So thank you for your attention. So this whole talk is based on, part of it is based on this recently accepted publication we have on sample size calculation for this one-arm trial with counterfactual placebo incidence based on recency assay. And the other part based on for the active control trial is an ongoing work with the same group of people. So thank you very much for your attention, and thanks.
Thank you very much for a very nice talk. So we have a few minutes for questions if there are any. I mean, we had a few already during the talk, so.
Yeah, I had a question, and thank you for the talk. I guess I'm curious about one of the assumptions underlying the method, and specifically the assumption that there's no difference between the HIV risk in those in the screening population versus those eligible for the trial. And I guess I'm having a hard time understanding why we'd expect this to hold, since HIV status is one of the screening criteria for the trial. And so like you would expect that if you're at high risk for acquiring HIV, you're more likely to be screened out. And if you're low risk, you're more likely to be included in the trial. So I guess I'm curious what you think about the plausibility of that assumption, if there's anything we can do about violations of that assumption.
Yes, this is really great assumption, a great question. And so basically here, when you say screening include like screening out those who are, so basically if you are HIV negative should be one criterion you want to screen subject for, right? But here by screening, we actually want to look at the population that is actually HIV neutral. And that is the setting where this approach can be useful, because we want the population to be HIV neutral, and then we look at those HIV positive subjects in there, and we apply recency assay to acquire the incidence for the population. So in that case, in that sense, we kind of modify this definition of screening a little bit, and actually that leads to a modification of this whole screening process. So for example, for current practice, usually for screening for a trial, usually the first thing you are asked for your test is whether you're HIV positive or not. And if you are, then you are just like entirely excluded from this, the rest of the screening process. But here, for this type of approach to be useful, the first thing will be like we want to include the subjects who are HIV positive and to be to remind them they're still part of the trial to contribute to this counterfactual placebo incidence estimator as part of the trial. So, and also there are other aspects of screening as well. So for example, I have mentioned about like, for example, other criterion like age, or like gender, or like if you have other chronic disease and other eligibility criteria related to the trial. So again, we want that kind of eligibility criterion to be applied before evaluating your HIV status, so that this no systematic difference between HIVs of those in the screening versus in the trial will be like more aligned together.
Okay, thank you.
Thanks.
Thanks. So any other questions? I see Adam is unmuted.
Faye, another question. Tom Fleming here. Thank you so much for a thoughtful presentation. I too have some questions about the assumption of rates in the screening population versus those in the trial, but I'd like to focus instead on some of what you were covering toward the end. And of those scenarios in non-inferiority, the one that made the most sense to me that you were presenting was the simultaneous requirement that the experimental is superior to placebo and that it's comparable to the active comparator. So I have a few questions about that. If I'm understanding, the power calculations that you did were for the experimental against active comparator, powering to it having a hazard ratio of 0.5, so having half the rate of the active comparator against ruling out 1.25. A little bit like what cabotegravir was against Truvada, where it was 0.75 against 1.23, and yet aggressive to assume 0.75. It turned out to be 0.35, even in MSMs. So if we're using, though, a cabotegravir control, then it would be particularly aggressive maybe to assume a 0.5. So that's question one. Question two is, I'm not sure why it's okay, as I think through it, to have an alpha-2 of 0.082 for that hypothesis. That one seems to be critical, that you are, in fact, ruling out that you're unacceptably worse than the active comparator, assuming that the active comparator has been shown to have an effect, meeting the constancy assumption. And then the third question is, how would this relate to kind of the traditional approach where we would just do a straightforward non-inferiority comparison like was done in 083, where it was a 0.75 against 1.23 in terms of size of the trial? So how does this approach compare to a 95-95 preservation of half the effect approach?
Yes, yeah, that's really excellent question. And I think actually, I feel like your first question and third question is kind of aligned very well, because I think one of the reasons, so for example, if you look at this table, where if we are looking at this first setting, like, so for now we ignore this issue of like alpha distributing a little bit. It's basically for, if we're only look at the second hypothesis, in that case, based on this sample size, we can really achieve a large beta-2, a large power. So in that, and also like this second hypothesis is indeed this hypothesis will test in non-inferiority trial. So I haven't done this calculation myself, but my suspicion is that here, based on this setting we're looking at, so if we look at only the second hypothesis, 1.25 versus 0.5, which is like, as you say, like here is may not be a reasonable, or like would be like a too bold number to use. So if we indeed have this type of setting, then this common practice of using non-inferiority trial will lead to a sample size that will be not that large or not that unaffordable. Because here, when we're looking at some like here, like even though the sample size of the alpha-2 is quite large, but we really have a lot of power based on this current sample size. So probably it's worth like doing some sample size calculation under this setting, such that we may have like another new row having that what is the sample size we'll use if we'll only consider the second hypothesis that it will be like the non-inferiority or superiority trial we're looking at. Another related thing will be, in that case, if my like suspicion is correct, in that case we don't need to use that much sample size for non-inferiority trial. Then probably that leads to another question, is that whether this setting will be something is really the main concern. So maybe the setting with the main concern will be, well, this null hypothesis will be like 1 or 0.75, as what you mentioned for the capital trial. So it will be the setting where we really have a quite competitive active control arm, and we will, based on non-inferiority trial, we will have we not have that much power. So in that case, we want to combine this counterfactual placebo arm to give it more signal. Does it make sense? So basically, as I have it stated again, so basically it'll be, so the setting having this weird result may not be the setting we want to apply this type of approach, because this type of setting are the settings where non-inferiority trial will be good enough to handle this problem. So we may consider a different settings, maybe like a different efficacy benchmark for the active control trial, active control arm, such that it is a setting we're mostly interested in, and it is a setting where adding up this counterfactual placebo will be of more interest, more use.
Yeah, it would seem others maybe have questions, but it's pretty aggressive to be talking about an alternative of 0.5 in a non-inferiority setting. I like your margin of 1.25. It seems practical that that's what you would have if you had confidence in a constancy assumption scenario and you had an effective active comparator. You'd probably only need about 50 events. Calculate that pretty quickly. But it would seem as though traditional 95-95 preservation of effect approach would be feasible in a setting where you are aggressively assuming that the alternative is having the rate against a really effective active comparator. My biggest worry going forward is if you're using cabotegravir as a control, or even Truvada with a high level of adherence, it's going to be hard for a new regimen to be half of that of the active comparator. And that's where creative new strategies might be helpful. Yes. It seems that this, though, could be a setting where it could be feasible to use traditional approaches.
Yes, yes.
Thanks.
All right, thank you.
Yeah, one quick question from Adam.
Okay, so going back to the assumptions, one of them was that you basically have this like fixed incidence. And I was curious, maybe there's two parts to it. So is it just really, because like, so if it was possible to follow up with individuals who were screened to have recency later on during the trial, you could actually test this assumption, but you could also, even if incidence wasn't constant, I feel like you could even adjust for that kind of using your framework. And is there any reason why you don't kind of try to just like estimate incidence in a different way?
Okay, thank you for that question. Yes, I think what your proposal is kind of related to another idea of counterfactual placebo and not listed here, that is to have a registrational cohort. So basically, there was an ongoing trial, like PrEP-BAC, I think. They were using that idea. So basically, they first register a number of subjects, and then, well, they have the subjects to, before the trial starts, to monitor the subjects without giving them any active product for a little time, so that in that period of time, you can actually see what's going on and like what's the instance in there. And then you can then give them like a new product, so that you can like slightly get around this issue, because maybe in a small period of time, you can have some subjects not taking product and some subjects taking product. So you can adjust for this maybe fluctuation of incidence over time. So here we want to make this type of assumption. Primary reason will be here. This screening is kind of strictly before this start of enrollment or start of given this new agent, so that it is something that's may be hard to address for this temporal trend since we do not have samples of subjects who are collected during the trial period. But if there is, then definitely we can try to adjust for that.
Yeah, and I guess to make clear what I was talking about before, you would so you would screen them initially, figure out if they were recent, but then you would follow up with them later, and then basically, if incidence is constant, you should expect every single time you follow up, kind of a constant proportion of those individuals you follow up with to fall out of being recent. So you don't like, these are all positive individuals, whereas kind of the other thing you were talking about, I think you would have had negative individuals in that.
I'm not quite sure if I understand correctly. We're not following those who are recent infected. Actually, we're not following those who are HIV positive, right? Because those who are
I was just saying that you could, if you wanted to test this constant incidence.
But in that case, you still want to follow those HIV negative subjects because those are where you can get information from, because you can only, for instance, when you have new cases, right? Like,
so maybe I don't understand, but so like you basically have this, let's say you can be recent for like a year, right? And so like when you test them, they're all recent, but kind of there's a distribution of times at which like they will still be recent. And so that should be fixed. And so if you followed up with just the recent individuals, you could find you could test this assumption.
So basically you test subjects like multiple times so you can have a better idea of when this infection did happen. Is that what you're talking about?
Yeah, and then you could see kind of like, is this recent, like, are these recencies kind of phasing out at a rate that makes it seem as though incidence is constant?
Yeah, that's a good suggestion. Yeah, that would be very useful, trying to have like a better estimate of when this infection will happen. And I don't think we have much time, but I was like, there's something related. So basically, if you have some prior test result of the same subjects, that will also help you to kind of rule out some infections and help you give a better estimate of like when this infection would happen.
Yeah, that's true. Thank you.
Sure.
Okay, thank you everyone for the great discussion. And let's thank again our speaker, Faye, and see you everyone next week.
Thank you.